This video will be about total internal reflection. I will directly start with a demo. In this demo, I have a magnetic whiteboard, and there is a red laser that has its beam very close to the board. In fact, some of the beam is reflected by the board so that you can see the beam. If I turn off the lights and close the door, you can see better. So essentially, you're looking at a ray of light. Then I bring in a piece of glass that has the shape of a triangle. And you can see the beam gets deviated at the interface. There are two kinds of interface, in fact, one from air to glass. Then the beam goes through the glass, and the other interface is from glass to air. Now, if I rotate a little bit the glass triangle, you can see that the refracted ray and the reflected ray are moving. If I continue rotating the glass triangle, at some point, you see that the refracted ray disappears, and there is only a reflected ray. Now, instead of a glass triangle, I put a piece that has the shape of a half disc. As I move the glass slower, you can see the refracted ray and the reflected ray at the interface between glass and air. In fact, if you look at the reflected ray inside the glass, it is reaching the other interface at the bottom, and you can see another reflection and refraction. Now, if I move the piece of glass even lower, then the refracted rays eventually disappears, and all the light is reflected inside the piece of glass. That is what is called total internal reflection. And so we will show that total internal reflection happens if theta A is larger than a certain critical angle that we will call theta critical. And this angle will be given by sine theta critical is equal to NB over NA. You see that because sine theta is always smaller than 1, the critical angle only exists if NA is larger than NB. As we saw in the previous video, because of Snell's law, NA sine theta A is equal to NB sine theta B. So if NA is larger than NB, for example, when light goes from glass to air, then theta A is smaller than theta B. And also because of Snell's law, if you increase theta A, you also increase theta B. But if theta B is larger than theta A, then it means that theta B will eventually reach 90 degrees before theta A. Right? So there will be an angle theta A critical for which theta B is already at 90 degrees. And because that theta B cannot be more than 90 degrees, then we don't have any refraction anymore above that angle. Then if I write Snell's law for theta A critical, then sine theta B is equal to sine 90 degrees, so it is equal to 1. So we have NA sine theta critical is equal to NB. And so that gives us sine theta critical is equal to NB over NA. Right. That's all you need to know about total internal reflection. So let's do an example of question. Let's say that you have an interface between glass with a refraction index of 1.52 and air with a refraction index of 1.0. What is the critical angle for total internal reflection in this case? Well, it is simply the inverse sine of n air divided by n glass. So inverse sine of 1 over 1.52. And if you calculate this, then you get 41.1 degrees. So you see that this critical angle is actually fairly small. Right? An example of application of this is called a pyroprism. So a pyroprism has angles that are at 45 degrees. So if the light in the prism comes to the interface with an angle larger than 41 degrees, then it will be completely reflected. So nothing will get out in the air, and all the light is reflected inside the prism. Right? So on this picture, you see a configuration where all the light is reflected and goes back in the opposite direction. That kind of pyroprism are used in binoculars, for example, to redirect the light to the eyepiece without any losses. Right? Not all binoculars have that kind of pyroprism inside. The ones that do they tend to have better optical quality, but they also are heavier. Now, there are other applications of poroprism. Apparently, you can buy that kind of glasses that have poroprism so that you don't have to bend your head to read your favorite book. I think this is kind of cool. Although I'm not so sure she's reading her lecture notes, right? Another example that takes advantage of total internal reflection is the fiber optics. You have a material that has a high refractive index, and the outside has a low refractive index. So the critical angle for total internal reflection is relatively small, and so as long as the fiber optics is not bent too much, then there will be total internal reflection inside. So the light will be trapped inside the fiber optics, and this is used to guide electromagnetic waves. Now, one more example. Have you ever wondered why diamonds are so shiny? What is it? Well, it's physics 9b. In fact, the index of refraction of diamond is very large. It's around 2.4. And so the critical angle for total internal reflection is quite small, only 24 degrees. And so if your diamond is cut with angles that are larger, then all the light is reflected back, and so that makes diamonds very, very shiny. Now, what about mirage? Guess what? It's physics 9b too. You may have seen this kind of mirage on the road. It looks like there is water on the road or something. In fact, this is an image of the sky. This is how it works. The light is deviated because of the temperature gradient in the air. The index of refraction of cold air is larger than for warm air. So if the air closer to the road is warmer, then the light from the sky will be refracted away from the normal, according to Snell's law. And so it will bend toward becoming more and more horizontal. And eventually, the angle will be larger than the critical angle, and so there will be total internal reflection. So the light from the sky will be reflected back up, and so for the observer in the car, it looks like as if the sky is on the road, right? But in fact, this is just a mirage. So here is another picture to explain what is going on. You can represent this temperature gradient by different layers. Each layer has a different temperature. So each layer has a different index of refraction. And then at each interface between two layers, the light will be refracted following Snell's law. Right? And eventually, there will be total reflection, and the light goes back up. And if the temperature gradient is inverted and you have warm air on top, then you can see an inverted mirage, where instead of seeing the sky on the Earth, then you see the Earth on the sky.